So yeah, I'm with Ozone Technologies. We're a company based in Western Canada. So basically, we've been involved with the NNEF converters. We're doing the converters for going to TensorFlow back and forth to NNEF, and Café2 back and forth to NNEF as well, using the protocol buffers. Quick background on the company. Company has been there for about 15 years, I think. They were mainly doing engineering services in the embedded vision space. And now we put together a framework for doing machine learning, deep learning solutions, and deploying them on embedded devices. So that's a high-level view of what we're doing. We have a software tool to entirely design deep learning solution on a laptop, desktop, to train a network model against a data set and optimize it for a certain solution. And then we export our trained model into our proprietary inference engine. So it's optimized to run across a whole range of embedded devices, from Cortex M4 to Cortex M7 and ARM cores. We have embedded GPU support as well with OpenCL. So today I'll just show you what we did with NNEF so far. Basically, we built an application which was running on the show floor during the exhibit. So we're doing ensign recognition at NXP's booth. So to do this application, I used our own software to do it. And I created it I tested the converter flow for NNEF. So I wrote it in TensorFlow, trained it in TensorFlow, converted it to NNEF, and from NNEF, I imported it into our tool, which converted it to our proprietary format. So it seems to be a lot of conversion, but in the end, it makes things much simpler. And for us, NNEF is a great way to enable our customers to use basically any available models made with TensorFlow and Café2. So those are screenshots of our tool. I'll switch to our tool. So this is our software there. So I just put together a simple example, importing a LeNet model, which was big enough for the ensign recognition. We tested it as well with Inception. It's working to convert to NNEF. For this specific use case, LeNet was big enough to classify ensigns. So just imported the model from TensorFlow to NNEF and then to our format. So our tool allows to visualize this model there. We can see as well the data set, look at different classes, images there. We can train from this workspace. It's using a TensorFlow background, TensorFlow trainer under the hood. You don't have to code anything. You just click there. It trains it. And we have a validation workspace to inspect how well the model is doing against the testing set. So we can inspect where the model fails and inspect which samples were not classified properly. From there, we can as well profile the network on embedded devices. So I brought today Cortex M4 right here just to show how it works. So if I click validate over here, what it's doing, it's using the train model that we built into the project. It's pushing it to the target. And then I'm sending samples one by one. It's running validation, and it's providing back feedback with detailed profiling information for each of the layers. So it's kind of quick and efficient way to design and modify network models, deploy them on different targets. On the show floor, we had a bunch of devices connected. Those were all available to test, so we could measure differences between like speed up of using a GPU versus a CPU version of it. So yeah, and using this workflow, I exported as well a train model, which is running at the back on the screen. So it's running on an IMX6 board. So basically the board has a camera. It's looking at a display over there with ensigns. It's running the classification and showing the inferred label. So yeah, this is what we have.
Yeah, okay. So yeah, me and Nicholas again from Axis Communications. We're going to talk about something we like call graphical VX. So we'll get to what that actually is, because it sounds very similar to graphs and VX, right? So Axis Communications, this is where we are located, or headquartered and founded in Lund in Sweden, in Europe. Yeah, so that's where we are on the globe. So what do we do? Axis Communications, you Google Axis cameras, this is what you find. We make surveillance cameras, all sort of security products, but surveillance cameras is the bulk of what we sell. We have radar products and other stuff as well. We make, the complete system from hardware to software. So yeah, security solutions. So yeah, some numbers. I think we're actually past 3,000 employees now. It's an old slide. We're founded in 1984 by a very talented engineer in Lund, and we've grown since then, or during the 30 plus years. We have a lot of partners, and we sell globally. We have some offices around the world. We do most of our R&D in Lund, in Sweden. So, analytics is how what me and Niklas do. We do some video analytics at Axis. We do some deep learning. We do some business intelligence. Yeah, a bunch of different applications. What we want to talk to you about today is video motion detection. So, spin around. See if this. So we do it on. This is just an example of what you can do with video motion detection running on the edge. Classical computer vision. So yeah, not super impressive resolution or anything, but this needs to be run at low latency. Low power, all that stuff. I'm sure you're familiar with that. So we want to process a lot of pixels to find moving objects, so we can do some tracking of them, and we can use this in video management softwares and start recordings or whatever. So trigger alarms. But we want to do the video motion detection, and we want to do it fast because it's quite a computationally heavy algorithms. So how does OpenVX fit into this? We've had two different, you can say, implementations of our this motion detection algorithm. We have our own proprietary vision accelerator. So then on our ArtBook chips, which you see here, one of our previous versions, the ArtBook 5. So then we need to write custom assembler. We write our own, so that can be super optimized, of course, but it's not very maintainable. Only for the 2 or 3 guys at the company who actually knows how to read that code. Fortunately, I'm one of those. So we have SIMD acceleration for our other chips, or older chips, which don't have this vision accelerator, or other chipsets we buy from other vendors. So yeah, Neon, V8MX. And we use a library, we use a C library, open sourced it. It's called RAP. Yeah, it has SSE and all that kind of stuff, other SIM processors. But so this essentially creates 2 different implementations, right? So yeah, need to speed on. We want to have portability. That's what OpenVX is all about, and we want to have one single implementation from an algorithm view. So this is a typical graph, as we've seen before. Slightly more pixely here, but yeah, from the specification. This example graph is from the specification document. So then the C code is pretty manageable to write. You see, it's not that too much code. Don't need to look at what this actually does. So when we actually want to express our algorithms, right, our motion detection algorithms as graphs, they became slightly larger. So this is one of our graphs. We have several different graphs in the algorithms. This is one of them. So And here's the resulting code for when doing that. So, yeah, this is just a snippet of the code. So yeah, it goes on like this. We can't scroll on this. But do you have something to say about this, Niklas? This sort of code?
Yes, I do. I think you should never ever have to try to write code like this. So and when you look closer at this code, well, the most of what's in this code is actually is connecting the nodes. So you have a lot of pointers you're setting up there, and you're connecting them, and you have to name them in funny ways. And after a while, it just becomes completely incomprehensible, and you're almost 100% certain you're going to make a mistake. So we thought this, let's not do it like this. So and then we started thinking, and when we started doing this, sketching these graphs, anyway, we started drawing them in some kind of drawing program because it's easier to read and easier to change and so on. So and then we realized that the format is quite comprehensible. It's quite easy to read. It's just some kind of XML-like format. So we thought, why not add some extra information in those nodes? A little bit about the formats and about how they're connected, the names and so on, the extra metadata coming from the standard, and then we can try to parse that. So the next thing we did was to write a parser to parse that code for us, that information for us, and then after that, the parser can auto-generate the code for that. And I mean, it's a standard, right? So the standard is quite well defined. It has its clear rules, so it's quite easy to write this parser even for the more generic cases. And the way we wrote the parser is also we wrote it in a specific way, so it should be easy to add new nodes. So you have a specific kind of a little file where you specify what information there is that this node about this node taken directly from the API, and the parser is designed around that, so it should be simple to extend. And then, since this is our new internal format for how we want to describe the graphs, we also create a small C library. We called it the Graph Manager. And then we realized there is also the graph manager inside of the OpenVX, so this is like a manager managing the other manager. But it's a higher level manager that is designed to read a few well-defined APIs to just set up and run the graph. And it's actually kind of similar to what we saw in this kernel import and so on, where it was also auto-generated and sets it up in a very organized way and had a few functions that you can call. So we saw a lot of similarities there. So now when you have that, you have the new sort of workflow runtime management becomes like this. You have the algorithm in one side, and you have the OpenVX low-level stuff on the other side. And so what you do is you create your manager, and then you have a graph that is generated by the parser. So you register that graph to the graph manager. You can actually register several graphs because this manager can handle switching between the graphs. When you register it, it also pre-verifies the graph, so you can have several graphs that are all pre-verified, so that you can quickly run them. And then you, for each iteration, you have to also register or set your input and output images, and then you can just process the graph. So it's all quite high level in this way, but it's enough to do quite general things. And then the remaining code that you still have to do is this is pretty much all the code you need to write. It still looks like a few lines, but really what they do is the first lines, they set up the input and output images, you register the graph, and then since you can have several graphs, you need to say which one is the active graph right now, and then you process, and the rest of the code is just setting new images. So it's very slim, very small actually. So this we like, but then there's an added benefit to this. So now, since we're anyway doing this in this graph thing, it's quite easy to add a little bit extra things. So that here's a part of one graph we used. So when you parse it, you can actually set up some checks to see if there's any mistakes you've done, because it's clearly specified in the standard how many inputs and outputs and which formats they should have and so on, which formats it can accept. So when we parse it, we just do a pass through and check that everything is consistent. And then we create what we call a validation graph. And this second graph, if you find any errors, it modifies the graph output and nicely illustrates with the red circles. Here's something that's funny, and actually even illustrates what's wrong, so you can go and try to fix it and see if that was indeed right. And once you fix it, it passes through and it gives you all green through, and it checks all the image formats all throughout. So what you specify is your input format and your output format, and then it parses through and it checks which valid formats you can have in the next node, and it checks that it matches the output, and then everything is okay. But so that's pretty good. But then we thought we have very large graphs at Axis. Yeah, just I'm almost done. So and so we also try to invent a concept called subgraphs. So you can many of the graphs were constructed from smaller pieces that were repeated many times, and so we had a system where you could loop and set them up and expand them into big graph. So with just these building blocks, we can create this big graph. This is the biggest graph we had so far. This one is something like 155 nodes. Most of these nodes are like and, or, those kind of binary operations. And it's kind of a motion search algorithm that does a lot in one go. And yeah, we wouldn't like to write this one by hand. It's just impossible. But let's see, I'm running out of time, am I? I have 2 minutes, yeah. So just to tie back to what we had before, we had the motion detection, motion tracking algorithm, and we want to accelerate that. And this is a pixel processing that was heavy, and it makes it so much easier to run on the embedded. So when you have when you look at the developer time, then for assembler it takes forever. So it gets better with the OpenVX. So it's already quite nice, but with the graph concept, it's actually really quick, and I think this is the way to go with this kind of standard. And the last slide. So that's for new algorithm. For new hardware, of course, it's a little bit different. It still takes a lot of time with assembler, but for the OpenVX, it's instantaneous because it's a portability. It's the same, and of course the same for graphical. But when you develop new things, it's really, really nice. Thank you.
Hey, good afternoon, everyone. I'm Mike Schmidt from AMD. This is my third time presenting here at this Embedded Vision Khronos workshop, and I'm going to briefly go on a little time machine back through what we've announced over the last couple of years. So we started a couple of years ago. We announced the first version of OpenVX that was open sourced, and here's some of the our design goals, and a lot of people are using that, and so we're really proud of that. Last year, we showed you this. We took and actually built an application using OpenVX. We built this application called Radeon Loom, and the whole idea was to be able to take a camera that we could film virtual reality and stitch together the images for all of the cameras in real time. And we actually used it for this movie, Bahubali. You can see it on the set over there being used, and I think it was right about the time of this workshop last year that we actually, the VR experience for that movie came out, and the movie was in the theaters. And these are some of the specs on what that product did. And this is what the architecture of that looked like. So the application sort of up on the top layers, and then we had OpenVX in the middle with some custom kernels and various other things, including OpenCL here, that actually ran on our GPUs. So this year, just like everybody else in the world, pretty much, we're doing neural nets. And this is a little bit of a diagram of what you might envision the workflow looks like for processing neural nets. So you can see you have some framework that you're going to train with, and you train, and now you have our interchange format. So we've implemented an interchange with NNEF as well as Onyx. And then those components over on the right are essentially our inference compiler, the model compiler. It's actually taking the intermediate formats that we accept and generating code that's OpenVX that allows us to then run on the actual deployed hardware. But it's a little more complicated than that. You really want to actually test your actual system, so I've added that in here. And even more important, things that finally this year people are starting to recognize as an important step in using neural nets for vision is that you need good data, right? And so that's sort of a part that's left out, and I'm going to show you some of the things that we're doing to help with that. But the steps in order to get good data, first of all, you need lots of data. Now, one of the good and bad things that's happened in computer vision over the last decade is that we have the internet, so we have lots of pictures. The problem is all these pictures are not well labeled. And even all the attempts at labeling them are still a little bit, I guess, in the infancy of this industry, because we've labeled a lot of pictures and everyone's taken all those labels as ground truth, right? As if, you know, it's sacrosanct, and that once it's labeled as ground truth, that people really think it's ground truth. I gave a talk 2 days ago at the summit, and when those slides come out, go look at them, because I'll show you a lot of examples of things that aren't very good. But today I'm just going to concentrate on just sort of quickly walking through these steps. Oh, got this. So you collect your data, you label your data, you do some analysis of it and make sure it's good. Then you send it off into your framework for training. You run your training on it. You get it into an interchange format of some kind. You then run it through a model compiler tool that generates your actual code that you're going to run on your target machine. You then put it on the target machine, and you run a bunch of test data through it and make sure that your application works. And then finally, you can deploy it and you can bring in live data. So that's where we think the overall workflow is. And one of the things we're trying to do is we're trying to enable people to do this and to try to ease a lot of the pain points. And you can see I've highlighted in yellow there where all the different Khronos specs come into play. This isn't where all of them come into play. This is just the places that was easy to annotate on the diagram. Okay, so what's showing here is we ran the inference here on about 9,500 images. You're not going to be able to see because I'm tapping instead of using a mouse, but we can see the summary shows how many images we ran, how long it took. This is running ImageNet kind of data, so you can see how many match top 1, how many match top 2, 3, 4, 5. I can go, for example, and look at all the labels that were found out of the 1,000 labels. I'm just going to pick one here because I got a couple of good examples. So if I just click on one of the categories, it instantly shows me all the images in that category. I can then sort it by whether they were matched or not matched. I can actually go click on these and actually see them, right? So this is an African chameleon that was found. I'm going to go to the top one here, which is an interesting one. This is one that was not found. Of course, chameleons are sort of like the hard edge case for computer vision because they're intentionally trying not to be found. Can anyone see the chameleon in this one, by the way? Yeah, so it's right here on the bottom of this branch. That's just sort of a fun one. But the idea of this tool is you can then go, and over on this right-hand side, I can see the confidence of each of the ones that were found. I can click on any of those, and it sorts by that value. And so you can easily find things that for example, were not found and had high confidence. And so you can basically use this to scrub your data and actually find all the mistakes in your data more easily. So rather than having training with some bad data, you can actually go through and scrub your data.
Hello, everyone. It's a great pleasure to come here. So to introduce one of the OpenVX vendors. This is Verisilicon. That's the company I'm working at right now. And the product, the VIP, as our product to support OpenVX. Oh, yeah, okay. So about the company, the Verisilicon is still a private-owned company, founded in 2001. Currently, over 650 employees. So 50% dedicated to R&D. We have multiple R&D offices and sales offices all over the world. So you can take a look at the whole company. And as for the VIP, I need to mention this is Vivanti is part of the Verisilicon and was acquired by Verisilicon. So the VIP originally from the Vivanti. So Vivanti is working on the GPU IP and the Vision IP. So we have VIP as our product name. It has multiple interpretations. So some people call this Vivanti. I think the marketing people call this Vivanti AI processor because AI is hot. Before, it's vision and image processor. So whatever. So basically, so many interpreters. But I think it's just like the meaning that VIP is very important for both the company and the customers and the developers. So we still call it a VIP. Probably that's not ambiguous. So basically, this VIP product line, we started quite early, probably 2014. And the first release is in 2016, the VIP 8000. And until last year, the licenses reached 10. I think it's more than 10 right now. It's quite beyond. So this is a basic introduction about the company and the product. So about the VIP architecture. Well, this seems like this seems like a lot. Basically, it has two founding blocks. One is software, and the other one is hardware. We started from 2014. Basically, because the Vivanti started from the GPU IP. We started from the GPU IP. 2014, early 2014, we start support of OpenVX. Try to use OpenCL or the GPU to implement the OpenVX. At that moment, the OpenVX is provisionally 1.0. It's quite early. And soon we found actually the standard GPU IP probably is not quite efficient for vision process. Then we enhanced the GPU IP architecture, adding the special vision instruction. We call it the CEVA instruction set to improve the efficiency. And even we can customize some hardware instructions to give a more powerful and the flexibility. So we feel this is good. And then we have started use this one to start working on the support of OpenVX. And also in the 2014, thanks for the Embedded Vision Summit. So 2014, so the summit invited Verisilicon to give us a great keynote speech introducing the convolutional neural network. At that moment, so we feel this is likely it will be big thing for the next few years. So we start working on the neural network support. Still, first start from the enhance the GPU IP instruction side, a bunch of things. And soon we realized this is something new. Actually, the GPU IP is focused on the vector and the multi-threaded. But neural network is naturally tensor. It's about tensor. It's about multi-dimensional convolution. So we created in the middle another module, another building block the neural network support, dedicated neural network engine. So right now we have two founding blocks. One is the programmable engine, starting from the OpenVX programming, and the other one is the neural network engine. We support this one even before we use the same framework, OpenVX framework. The concept, the graph concept and data flow is great, it's natural. We use this one and support both. This is the, I think we can call it the two fundamentals to start a VIP architecture. Probably we can credit the VIP founders to OpenVX and the neural network, embedded vision. And okay, so this is the VIP, basically the architecture features right now. We can support OpenCL, OpenVX, that's the fundamental major blocks for the software stack. Even for the, we have so many frameworks to support. Later on, we have, we can all this convert back to the OpenVX execution model. So this is pretty much the basic structure. And as for the scalability, we added the third part, the module is, it calls it VIP Connect. So it allows the third-party fixed function module to plug in with some interface flexibility. So this is the basic architecture. Software-wise, well, I still need to emphasize that the OpenVX from the day one is one of the major fundamental blocks for the software stack. The frameworks, all the frameworks convert to the OpenVX. Even for the neural network support, we started using OpenVX. At that moment, we don't have a Khronos extension yet. We just use the same very basic OpenVX framework concept to extend the support by using the vendor extension. So thanks for the OpenVX flexibility framework to allow all this happen quickly. This is from the hardware point. We have built, so two founding blocks. The vertical is the program engine, so we can scale up quite well. And the horizontal one is the neural network engine. We can also scale up. So this gives the customers, clients, partners the basic, a wide range of matrix configurations to pick. So it can cover a wide range of use cases and the scenarios. Except for the basic hardware and the software, architecture, stacks, system software, we also improved the two sides to enhance the user experience. We call it the Acuity. Basically, it's the map to convert all the framework models from float32 to integer A and optimize. This is quite just like other vendors. So we have these two sides. It has, I need to mention this is, you can do quantization. Conversion is a basic function, and you can do quantization. You can do pruning. You can also even do some fine-tune and retraining to restore the accuracy. This is the IDE part. We can do this to give a better user experiences and to how to manage the OpenVX projects, even do the profiling and the debugging, set breakpoint, debugging. So all this stuff, just I think I need that's all. And we have an office very close to the convention center. You can welcome to visit. And we can, over there, we can show the VIP demo. We don't have a demo set up here, but over in the office, we can have some setup for the customers and the partners as treated as a VIP guest. We can use it to show the VIP demo. That's all. Thanks.
Yeah. My name is Andrei Turetsky. I work in Cadence Design Systems. Cadence has its own OpenVX implementation targeting Tensilica Vision DSPs. During last year workshop, Frank already told you some basics about Cadence and OpenVX implementation. So I would like to go deeper into details and tell you about our image tiling technique and why it improves vision application performance on our DSPs. And also I would like to tell you about our vendor extension called vendor custom kernels, or shortly VCK. So let's start with styling. In Cadence DSPs, we have tightly coupled memory to achieve lower power and higher performance. We call it local memory. This memory is very small, but core can access it in a single cycle. However, the memory transfer from system memory to this local memory is done through DMA engine, which can work in parallel with the core and usually have multiple channels. So since this memory is small, while executing OpenVX graph, we can't just put the whole images there. What we can do is we can put images in a set of sub-images called tiles, which will fit local memory, and we can run the graph per tile. This technique called tiling. It's a complex technique, and we need to know lots of information like kernel specifics, local memory size, operation connectivity. But due to OpenVX graph-based model, we can do this, and our implementation does it automatically during graph verification step, which means we have small runtime burden. Of course, not every kernel can be tiled due to algorithm complexity. So now a few words about optimizations which can be done with tiles. So to achieve every high-performance system tries to minimize memory access waiting time. So in context of Cadence implementation of OpenVX and DSP is done through parallelizing of core computations and memory transfers. This is done through ping-pong buffers. So the main idea is to have two buffers per tile. One is used for core computations, while at the same time the other one is used for memory transfers. This way, we can do computation on the current set of tiles while storing the result of previous computation and loading a new set of tiles for next set of computations at the same time. Again, this if kernel is tileable, all of this is done by our implementation of OpenVX automatically. Now we can draw some simplified charts which shows us dependency between tile size and DMA, memory transfer time, which is red line, and core computation time, which is green line. Of course, it's very simplified because in the real life there are not straight lines there, more complicated functions, but as a model to show how we can improve tiling, it works just fine. So to the left, you can see a preferable case where green line crosses red line. To the left of a vertical dashed line, which shows maximum tile size, which is based on memory, local memory capacity. So in this left case, we can choose tile size big enough in this within this green zone, so that computation time is longer than memory waiting time. That means our core can do computations without interruptions. Of course, very often we see different cases, like, for example, in the middle, where green and red line cross to the right side of the memory limit line, which means we just can't choose the tile size big enough, and we have to wait for DMA memory transfers for some time. Or the worst case to the right, where, for example, kernel has a very simple algorithm, and it's executed so fast, DMA waiting time is much more, always much bigger than computation time. But there are some techniques to make cases to the right, to get them and transfer them to something closer to what is on the left. For example, one of this technique called type shaping. Basically, it's when we know DMA engine parameters, we can choose tile size so that we would minimize data transfer time. And that would make the red line more flat, which is good, so that there are more chances so that the green and red line cross within memory limits. Again, for tileable kernels, this is done by OpenVX automatically. Developers don't need to think about it. Another technique is tile chaining. So this is basically optimization of OpenVX virtual images. If you have a subgraph which is connected by virtual images, we don't have to go to nodes one by one and load tile, execute node A's and load next tile, execute node A, and so on, and then go to next node. We don't have to do this. We can just download a set of tiles for this subgraph, compute all the nodes, and then go to the next set of tiles. That would increase computations, amount of computations per tile, which makes green line on the chart more steep. Again, that's good. That means there are higher chances to cross the red line in the memory limit zone and avoid DMA transfer waiting time. As a downside, it can reduce tile size because since we gather more nodes, we might need more buffers for tiles, which means tiles should be smaller. So that's some kind of trade-off. And again, all this done by OpenVX automatically. Now, a few words about VCK. So VCK is a vendor extension of OpenVX, which extends user kernel concept. The idea is it provides a mechanism for developer to run custom kernel on the DSP. This DSP can be tileable, and it participates in all tiling-related optimizations I just described. OpenVX will take care about ping-pong buffers, tile shaping, tile chaining, and DMA transfers automatically. VCK gives to developer freedom to choose kernel implementation. A developer can choose to use some existing library like OpenCV. It will be a simple approach, but it will give lower performance. Or a developer can use our libxi library, which provides hundreds of highly optimized kernels for our DSPs, middle complexity, middle performance. Or developer can write its own algorithm and add custom hardware to the core during Verisilicon instruction extension, which is a very log-like language, and get the best performance. And just the last slide. So how we configure core. So developer can choose basic core, for example, P5, P6, or Q6. Then he can add some additional options, for example, additional local memory size or additional instructions to execute the algorithm of VCK faster. And finally, as I mentioned, using TIE language to add some customized hardware to processor, more complicated computational units, and so on. Thank you.
Hello, everyone. So I've got a few talks this afternoon where I'm going to talk about some of the open source and standard stuff. But this is the sales pitch of what my company does. So I'll go into some of the technical details of some of all of these things, but at least so you can see how we make money. So Codeplay provide industry standard solutions for connecting AI software with AI processors. We were actually one of the pioneers of doing graphics processors. So many years ago I started Codeplay, and we did one of the first, it's 18 years ago or something, yeah, we did the first C compiler for graphics processors. So we've been doing this stuff for a long time. Originally video games, I'm from a video games background, but almost everything we do now is AI. And so generally for our customers, they're chip companies, and their customers what we're seeing a lot of is they've designed a prototype with NVIDIA GPUs, often with quite big, expensive, power-consuming NVIDIA GPUs in a desktop, and someone's going, oh yeah, why don't we run this on a battery and make it really, really low power and safe enough to drive a car and all of that stuff. And these people now want to produce a high-volume product, and there's a lot of companies out there that want to win the business of providing that AI accelerator for all of those applications. And so our approach is to provide minimal disruption to one of those customers. So if they've designed their code using CUDA, we're going to make it very easy for them to port it across to an industry standard. We do use industry standards for everything. So the industry standards we use are OpenCL and SYCL. So I was quite involved in the OpenCL group. I'm quite involved in standards, and I push SYCL quite a lot because when we did the first video game compilers back in 2001 or something, all the video game developers said we don't use C anymore, we use C++. So I pushed very hard for us to standardize C++ as an accelerator programming model. And what we do is actually we provide high quality modular components to building together solutions. So often people build chips out of bits of different IP blocks from different vendors, try and combine things together. So we operate entirely in terms of different components that fit together and communicate via open standards. One of the big things that persuaded me to go to open standards is in the early days we'd do specialist compilers for each processor. And by the time we'd finished the compiler and then people had ported their software to this special programming model that we'd done for the processor, you on to the next process node, so the processor was completely obsolete. So we as a company have been going for quite a while. We got funding from Jez San, who was quite a well-known innovative 3D video game developer who started a company and went, why don't we just design a processor for this? And so in the late 80s, early 90s, they designed a processor that became the Super FX chip in Nintendo. I don't know if you remember those days. You had cartridges with chips on. You know, you didn't download games off the internet. The cartridge with the ROM chip in, and they went, why don't we just stick a new processor in there to do 3D graphics? Very recently, obviously we've designed all of this stuff for doing video games, and people said, you know, we want to actually drive cars with this stuff, which is quite terrifying. So we very recently got a bit more investment from an investor you probably haven't heard of, but you may have heard of Williams. So the Williams Advanced Engineering is the consultancy arm of the Williams Formula One racing team. And they do lots of crazy automotive projects. They're very innovative, and this year is we don't actually deal with the Formula One team. They haven't done Formula One cars, but the consultancy arm does stuff like they design the electric chassis and batteries for Formula E. So all of the Formula E cars use those. And we're doing some stuff. Battery monitoring is crazy. I had no idea what an incredibly complicated thing is. Very involved in the standards foundations. I shouldn't mention any other standards foundations, but there are other standards foundations around. And actually, publicly, we support ARM Mali, Renaissance Archive. I've got a very simple demo over there, but I haven't got a power adapter for the monitor, but I'll show you. And we support AMD GPUs and Intel CPUs and GPUs, and we've got a whole load of other processors support coming for all of the stuff I'm going to show. So we're very involved in Khronos, chair the SYCL group. I used to chair the SYCL group, handed over to Michael Wong, who's on the C++ committee, so he understands this stuff much more. And HSA Foundation, BSI is the British one. MISRA is a big one for us because we need to be able to define safety standards for this. And MISRA is one of the safety standards for C++, and it's quite old-fashioned, and we need to update it to be able to support ADAS. But what we're also trying to do, and I'm going to talk more about this later in my later presentation, is we're trying to get all of this stuff into ISO C++. So you don't even need a special standard. You just use a normal ISO C++ compiler, and it will just offload to your whatever accelerator it is, whether it's an FPGA or a vision processor or whatever. So in terms of what we are as a business, we provide a mixture of products and services. So our products are implementations of some of these open standards like OpenCL and SYCL. So if you've designed your own processor, we can sell you off the shelf most of an OpenCL implementation, and then what we do is combine services together like compiler development, debugger development, and stuff like that. And we do it for lots of stuff. We actually do quite a bit of open source stuff if you look around, but also lots of implementations of OpenCL and things and other things will have been built by us. We ported CodeXL, which is going to be open source. It's not yet, but CodeXL is AMD's open source profiler. They kindly open sourced it, so we thought we'd port it to other platforms. And I'm going to talk about all the TensorFlow stuff later. But basically, this is something that we noticed in looking at how most AI processors look today, this is a massive simplification of it to fit in a slide, but they're pretty much like this. So you've got some on-chip memory, you've got some convolution hardware, you've got some matrix multiplier hardware, and you've got some kind of programmable AI processor, which may be a GPU or maybe some kind of DSP. And basically, you know, the rules of physics are the same for everyone, which is that you need to keep as much data as possible on chip. If you go off chip, it hugely hits your performance. So if you look at most AI software, unfortunately, it's not written with Khronos open standards. It's predominantly written with NVIDIA. NVIDIA have done a fantastic job. I'm going to show you later just how much of a good job that they've done in a way. But you write it with cuDNN, cuBLAS, or CUDA C++. And so the question is, how do you map those two things together? Do you ask people to rewrite their software, or do you just go, why don't we just map it to open standards? And so that's what we're doing with SYCL. We're building out open standards which give you the same level of programmability you would get with CUDA, but with open standards and open source software. And it achieves pretty much the same thing. It gives you as much as possible on the accelerator. It allows you to use your hardware. It allows you to reduce your memory bandwidth. But it's all open standards. It's easy to move around. And the next question, of course, is where do we fit in? We can help you deliver it for a new processor. So if you're designing a new processor, we can provide the compilers and the backends and drivers. So we have really good compiler developers. We've built up a team of LLVM backend developers. It used to be if you did a Google search for building an LLVM backend, it would be our presentation that came first, but someone did something else. It's second now. And then we have Compute Auto, which is our OpenCL implementation, and Compute CPP, which is our SYCL implementation. And then top of that, we've got a massive ecosystem of technologies around that. And I've got 10 seconds. That's basically what Compute Auto looks like. That's the architecture of it. If you want to build your own OpenCL, that's what you have to build, all of those things. I'll leave it there because I'm going to be talking more this afternoon.
Hello. My name is Yair Siegel with CEVA. For those of you who are not familiar with CEVA, we've been licensing IP since 1991. Very successful in the mobile market, and in the last couple of years, since 2011, we've been licensing IP for computer vision and for AI. So we have over 40 design wins for a combined. We have already about 4 generations in the market now. The latest one is NeuPro, which is an AI processor, and it also combines support for computer vision as well. You can see here some of the markets that we're playing in. So we have various markets, some products already in the markets. For example, we have stuff like mobile phones that came out with our processors, drones, automotive dash cams, 360 cameras, and more. So they combine today a lot of computer vision and starting to have neural networks in them. Here you can see basically a high level of our solution. So we have a combination on the right-hand side of a hardware solution that combines a DSP processor, very good for vision, and also a variety of accelerators for a neural network, which include multiple generations, just convolution and full AI processing. And then on the software support, we supply a variety of solutions, including tools, fully programmable from C++. And then we also supply software tools for a neural network. We have our own framework called cuDNN, I'll explain in a minute, and also support for computer vision as well. So for the neural network, we came out in 2014 with a tool called CEVA Deep Neural Network, or for short, cuDNN. So this tool automatically converts any framework, any network in different frameworks. So we started out with Caffe and TensorFlow, and we automatically convert the network into more appropriate network that is fitting for our processors for inferencing on the edge. And this is done by a push-button framework. And this is already being used by many partners and designers. And then for the computer vision, we have a full solution that enables to basically offload processing capabilities from the host side onto the computer vision processor, the CEVA XM family. And essentially, we have been working on our OpenVX implementation. It's still not fully certified, but we have been doing our computer vision and techniques for quite a long time. So essentially the idea is to take an OpenVX framework to repurpose it to the target of the CEVA DSP. So we have a VX wrapper around underneath the framework, and then send it through from a CPU side through dedicated mechanism which we call CEVA link to the XM processor, and then there we have also VX wrappers, and eventually it is modeled either to the CEVA computer vision libraries or to developer libraries, which are also optional. Developer can add his own libraries and then add the wrappers to implement them and call them from the host side from the VX application. So this is part of a full solution that we have. And that's basically it. Any questions we have, or we can also show a demo. We have here a small demo running in real silicon. Thank you.
So I have a question. There was a few people, companies that have almost implementations of OpenVX, but not certified as compliant yet. And I wondered if you guys had any comments about when or whether you might do that, and what version of OpenVX you would support as a compliant.
I'm guessing that's to CEVA.
So it really depends on the market. So, we actually joined Khronos, when was that? Maybe 2013, 2014. So we were very anxious for the OpenVX to ramp up. And actually, we had an implementation which was very similar to that even before that, for 2012. But, it's really up to the demand from our customers. So we have over 40 customers, but so far, we've been delaying the implementation, not because it's hard or anything, just because the priority has gone to other things. So really up to the priority we get from the direct licensees.
Thanks. I'd encourage you to go ahead and submit something as far as the speaking as the chair of OpenVX, promoting and showing on the adopters page. More the merrier. It'd be great for the standard.
Hi, question for Codeplay. I have a video, DJI panel for video, and then I integrated the thermal cameras. So I need let's say I buy the NVIDIA this board. What I need to do, I need to inspect the railway tracks. Let's say I have the some of the videos. Is it this processor or this hardware will support?
So I think that what you'll find is that on the desktop, it is the GPUs that you can use, and the desktop GPUs will be able to process videos pretty much. I think what we find for our customers is, what we're showing over there is a Renesas RCAR product where we're doing OpenCL for that, and we're demoing OpenCL running on one of the tiny little vision processors in there. And it's just a demonstration that you can run software on lots of different low-power devices. But I would, if what you're talking about is desktop, like you're processing on a desktop, then the GPUs are pretty good for that. It's going to be pretty hard to beat that. Well, where we get involved is where people start to put things into much lower power consumption. And when you want to get much lower power consumption and higher volume, you write quite specific processors for individual tasks. So you'll have a processor that's good at doing video, and then you have some processors that don't do video. And that's where the kind of variation comes and the power efficiency comes. So I'm not sure if I've answered your question, so I think it may be more detailed than that.
Okay, sure. I'll send an email to you and get more details. Thank you.
Just a question for the Axis guys. A really cool tool that you presented. Is that ever planned for any sort of external facing tool or software release? And B, for the validation that you're able to do, it looks in some ways more sophisticated than what you might get just by running like verify graph, or maybe it's easier to add validation checks in Python or whatever tool you're using. is that true? And like, how did you approach that kind of out of the non-OpenVX validation via the spec, or if what I understood about your comment was true?
If I understand your last question correct, I think it's easier to do it before. I mean, it's for debugging purposes. I mean, it's easier to debug when we have the in our Python format we have node by node. Otherwise, you would get these errors when you do verify graph, right? So then you have a big graph that's connected, and depending on the implementation, if you have an implementation which has really good debug opportunities, then it can be as easy there. But yeah, we found that we caused at least many mistakes that we spent time debugging otherwise, which we could catch quicker, like this. So yeah.
Yeah, and like if you're at node 1000 and you
yeah,
verify the graph,
yeah,
and
exactly.
it doesn't verify. It's like some. So you do each one separately, and does that involve like parsing the C or?
Well, okay. So in our tool that we have, we use.
Oh, you're generating this. Yeah, never mind.
Yeah, exactly. Yeah. So yeah, if we get an error in there, then we have some error in our parser or something. Then yeah, that we need to debug, but we haven't. I mean, it's pretty straightforward for format connecting the nodes, so we haven't managed to screw that up yet, at least. And yeah, speaking of
I mean, what we're parsing is the XML that or graph ML that comes out of the graph program, and then we have for each node we have read the standard, and we have checked the most important things that you need to have right, and those we have written checks for those. And since it's quite modular, those checks are per node basis, so it's quite easy to implement without getting too messy code. There was the first part of the question.
And is any of this external facing? Is this all internal tools for you guys, or do you sell it or publish it in some way?
It was developed as an internal tool, but I can see that it might be interesting for others too. So it's interesting to hear from people here if they would be interested in such a thing. We haven't really talked about that too much internally, but we could bring that message back to our managers if it's interesting.
Any more questions? Oh, I have a couple of questions that I want to ask. One is to A-Zone about NNEF implementations. I think this question popped up during earlier discussions, which is if you're trying to move from, let's say, TensorFlow into NNEF, and there is the issue of TensorFlow does a lot of the stuff underneath cryptic that cannot be represented in NNEF. Now, how are you going to handle that?
Well, first thing to mention about that is that any TensorFlow model that will be supporting will need to conform with the NNEF supported operations. So basically, when building a network in TensorFlow with the goal of exporting it to NNEF, it needs to match the supported operations. But with that in mind, it makes it possible to do that conversion. And the converter will also clean up the graph. It will clean up everything that's not required for running inference. So typically the protocol buffers from TensorFlow will be much, much bigger than what's required to run inference. So the converter will kind of clean this up and keep only the required operations for running inference. So does it answer your question? Or, yeah.
Do you require frozen graph?
Yeah. The existing converters, like you're writing code in TensorFlow and then you can convert to NNEF. What I'm working on at the moment is frozen graph from TensorFlow to NNEF. Just to avoid the dependency on the TensorFlow framework. So you can convert only with the NNEF converters without installing the frameworks.
Thank you for that. Any questions?
Sorry, I missed your presentation. Can you give a little bit hint on Cafe 2 to NNEF? What is the plan? I know you guys are working on it. So.
Yeah, it's the same. Like we're working at the moment. I did a proof of concept on TensorFlow. We're halfway there with the TensorFlow converter. Right after, we'll be doing the Cafe 2. So sometime this summer, should have support for both frameworks. And yeah.
Okay, thank you for that. I think I have one more question to Cadence. This is something I was still not able to figure out. I think I had a similar question I heard. Cadence provides an OpenVX implementation as for an IP, right? Now let's say there is a system integrator, somebody's building an SoC that uses Cadence IP and somebody else's IP. Let's say all these IP vendors are providing OpenVX. How would you expect somebody sitting on the top level, let's say they're also providing an OpenVX implementation, how do you expect this whole pipeline, basically top level scheduler going to the low level scheduler? How do you see this communication and scheduling happen? Okay, so let's say there is a vendor who's trying to build a system on a chip. And on the chip, they have Cadence IP and maybe some other vendor's IP. Both provided their acceleration using OpenVX API. And the company which is building the SoC also wants to provide an OpenVX API to their customers. Means it's not just chip level, right? Let's say when somebody's building a system, there's a GPU vendor who provided OpenVX CPU, and kind of somebody's building at a top level system integrator. So if every component vendor are trying to provide an OpenVX implementation, what's the path you provide to your customers to be able to implement OpenVX on top of your OpenVX?
Actually, I don't think we. Oh yeah, if Frank can answer this question, yeah.
Yeah, so as when we had this question before, the spec is really an API for the programmer level, and what you're asking about is at the IP or the SoC integrator level, and how do I pull in all of these IPs and things like that. And the spec itself doesn't really address this, right? It's really for the application developer writing software. So you do have to work with your IP vendor. If you're an SoC vendor and you're integrating all of this stuff, you need to work with your IP vendor to figure out, what you're going to run where and how you're going to have sort of a graph manager that knows how to distribute things. And so we provide a Cadence. First of all, if you have licensed the IP, we provide the entire OpenVX implementation in source code form. So you can take that and add that however you want, add whatever you need for other, and so that's a base starting point. So if you have other IPs that do some portions, you have an accelerator that you've added, or even as Andre was showing you, we actually have this language that allows you to add your own instructions to the DSP that can, and you can take that source code and add whatever you need for that. Also, another thing that we've done, say if the SoC vendor wants to sort of, they have their own sort of graph manager, and they want to plug rather than taking our code and plugging into that, they have their code and want to plug us into them. We have an interface, and it's not a public interface, but it's something that we work with SoC vendors where we say, we describe our operations and something about their inputs and outputs and performance, and then that interface can be used by their graph manager to do the scheduling. So we offer both ways.
I have a question. Not sure, not specific to any company, but some of the companies use GStreamer to do their image processing and streaming. How does that play with OpenVX, if anybody can comment? Nobody.
Frank, you should be here. You're the chair. You better be here.
The ringer. Anyway, so GStream. Well, the OpenVX API is really a compute API. So what we kind of assume is that the image is in memory somewhere, and then we start computing on it. So how it gets there is not really part of the standard. And so when people are doing their development, because we don't know what the hardware is out there for doing the capture and whatnot. But it has been the case that you can use GStreamer and connect up to say, oh, look, I've got this stream of images. And I know of at least one company that did this. I don't know if I can say that name, but there is a company that's done this where you just say, look, I'm hooking up GStreamer as the front end of the image. It's providing stuff. So it's kind of orthogonal. At least the OpenVX standard was designed to be orthogonal to that, how you get the images.
My line of thought was around the scheduling and how scheduling can work with GStreamer. Again, Khronos doesn't deal with scheduling per se.
Well, right. So the implementation has got to figure all this out. That we just provide the infrastructure to enable those implementations to do the right thing. But this extension that we just had this year, this pipelining and streaming can help with that too. So that you know that a sequence of images are coming in, and yes, your implementation has to do the right thing. But we hope we've given all the right hooks to enable you to do that.
Any other questions? No? So I think we have 4 more minutes, but I think we can close. We got a half an hour break now, and all the presenters are going to be here, so feel free to ask them. And also there are demos back there. Maybe the companies who have demos, do you guys want to tell what demos you have? Maybe that'll give us people to come back to the demo booth later. Want to tell about your demo?
I just have a very simple demo. Apparently, all of the other demos were busy, but we've got the RCAR platform, which is the automotive ADAS thing that we're for pedestrian detection and stuff like that. So we've got OpenCL running a very simple vision application on there.
I have a short demo demonstrating Venner custom kernels extension. Just a simple image blend kernel, which is not an OpenVX spec.
Our demo is running on a real-time silicon for a neural network for object recognition.
Which demos do we have back there? I don't know. We don't have that running today. It's at the booth. Yeah.
Okay.
Yeah. We had a demo yesterday at the booth, but not here.
Yeah, so as I mentioned during the presentation, I have American Sign Language classification. It's a really simple network. It's really just a proof of concept of going through the converter using a train model in TensorFlow and deploying it to a real target. So it's classifying and sign over there.